So good morning. So now we are going to look at heap sort. Okay. So before looking at heap sort, we need to look at what a heap data structure is. Okay. So a heap data structure is actually a complete binary tree. Complete binary tree, remember we've said, is a tree, a binary tree with uh, when you're filling the nodes, you fill one level at a time from left to right. That is what we do in a complete binary tree. Okay. So a heap is a complete binary tree, and plus it has to satisfy the conditions for each node n in it. The value at n is greater than or equal to the value of each of the children. Okay. A heap is a complete binary tree with another property that if you take any node, its value is greater than or equal to its children. Okay. In the case of binary search tree, we said if you take any node, the left child is lesser than the node and right child is greater than the node. But in the case of a heap data structure, if you take any node, its value is greater than or equal to its children. That is a property. Okay. Now this is, you can have both a max heap as well as a min heap. Okay, max heap means, that is the definition we said. That is, if you take any node, its value is greater than or equal to its children. And the case of min heap, if you take any node, its value is less than or equal to its children. So you can have both a max heap as well as a min heap. Okay, right. Now, okay, so how do we represent a heap? So heap is a complete binary tree, right? So you can have either an array representation or a linked representation. But here, since heap is a complete binary tree, we are going to have an array representation, because in the case of a complete binary tree, we know we are filling the values from each level. ഒരു ലെവലിൽ നമ്മൾ fill ചെയ്തിട്ട് then and within that itself from left to right. So if you take a complete binary tree, we have already seen that it will be filled completely like this. Okay, നമ്മൾ complete binary tree എടുത്തു കഴിഞ്ഞാൽ നമ്മളെ values root will be at 1 and its children will be at 2i and 2i plus 1. അപ്പോൾ ഓരോ ലെവൽ ആയിട്ട് നമ്മൾ fill ചെയ്ത് വരുന്നതുകൊണ്ട് this, if you use an array for representing that complete binary tree, you will not have any blank spaces. Okay, so this array representation is actually more efficient for representing a heap. Okay, so here we are assuming an array representation for heap. Okay, now we look at insertion of elements into a heap. Okay, if you look at this is a max heap. If you look at any node, say 95, it has a value greater than its children. Or if you look at 75, it has value greater than children. 85, look at, okay. So this is a max heap. Now how can I insert elements into this heap and ensure that there is no violation of the heap property? Okay, so since this is a binary search, since this is a complete binary tree, the next node we are going to insert will be as a left child of 25. Okay, so here if you look at this example, left child of 25, you are adding 19, let us say, for example. Okay, so you are adding 19, and what you do is you check, we know that all the other nodes are actually satisfying the heap property, which means the only violation which is possible is here. Right, only violation which is possible is here. So you have to check 19 and its parent. So when you look at the parent of 19, we see that it has a value greater than 19. So which means there is no violation of the heap property. Okay, so which means this is okay. Now let us say we are going to insert 111. Okay, for 111, if insert next point you're going to insert will be as a right child of 25, because this is a complete binary tree. Complete binary tree means you're filling nodes from left to right in a particular level. Okay, so here you are adding 111 here, and if you look at 25, the parent of this, you know that there is a violation. So what is done is, since there is a violation, you swap 111 and 25. Now 111 comes here and 25 comes here. Okay, that is what is. So 25 is here. Okay, we'll take red color. And 111 is here at this point. Now again, now this node has been changed, so its parent also you have to check. And we know that in the case of an array representation, you can actually go back to this parent using I by 2. I by 2. If you take the I by 2 index value, at that point you will have the parent. So you look at the parent 111 and here you have 85. So 85 is lesser, so you have to swap 85 and 111, which means again you have to cut this and 85 comes here and 111 comes at this point. Now the possible violation is with this parent. Again you compare, you have a 95 here, so you have to swap 95 and put 111 here. So when you do this, the heap property is satisfied. So basically you're following from the node where you inserted the value, you look at its parent, its corresponding parent, and you follow the path until the root is reached. So by that time you will have all the violations gone. So this is the resultant heap tree. Okay. So this is how you insert values into a heap. Now we'll also look at the algorithm. So here item is the value to be inserted. N is the number of nodes or number of values which are present in the heap. Now item, the output is this item is inserted in heap tree, and array A is where you are actually where you are actually keeping the tree values, okay, or the values in the heap. And the size is the max size of the array. N is the number of elements in the heap. Okay, now if n is greater than or equal to size means you cannot add because the heap is full now. Okay, otherwise, if not, then what you do is, so we said we are adding as a rightmost element, which means that is till one point it is full. So rightmost element will be the next blank point. Okay, that is where you will add. So what you do is n is equal to n plus 1 and then you add your item there. Okay, അപ്പോൾ item നമ്മൾ ഇങ്ങനെ ഇപ്പോൾ 19 ആണെങ്കിൽ ഇവിടെ നമ്മൾ കൊണ്ടുവച്ചു last item ആയിട്ട്. Okay, we are just simply inserting it there. And next what we have to do is you have to check whether that item violates the heap property. For that you have to check with its parent, right? So I is equal to n now and p is equal to I div 2. That is the parent index. Okay, now you are keeping this as long as p is greater than 0, that is it is a valid index. Indexes vary from 1 to n, right? And if a of p is less than a of I, that is parent in the value, if it is less than that of the item which we have inserted or the current item, which means there is a violation and you have to swap. Okay, so these steps are actually swapping the parent and the current index. Okay, swapping the values. Once you swap the value, you have to check whether its parent, that is, you are again setting I is equal to P and P equals P div 2. നമ്മൾ നേരത്തെ പറഞ്ഞ പോലെ here, that is, you are swapping this and this, then you have to check whether there is a violation between this node and its parent. So you have to repeat that, right? So that is why you say I is equal to P and P equals P div 2. Keep repeating until either you reach the uh, mm, root വരെ നമ്മൾ പോയി കഴിഞ്ഞാൽ there will be no violation or index is 0 ആവുന്ന വരെ. Okay, so keep repeating. So this is how you insert values into a heap, right? Now about, okay, so we know what a heap is. Heap is a complete binary tree with the additional property that if you take any node, its children or the node will have a value greater than or equal to that of its children. That is the property of the heap. And we know how to insert values. Insert values ചെയ്യുമ്പോൾ heap property violate ചെയ്യുന്നുണ്ടോ എന്ന് check ചെയ്യുന്നു. And if it is violated, you keep swapping until the root is reached. Okay, this is what we do. Now we move on to heap sort. Okay, heap sort means any sorting algorithm means we have a set of numbers which are given to us, right? We have a set of numbers given and you need to sort it. Okay, in the array we have a set of numbers, let us say. So given a set of numbers, first thing we have to do is we have to build a heap from it. Okay, so how do we build a heap? Say for example, Okay, let us say 23, 45, 67. This is sorted. 23, 67, 45, 1, 11, 99. Okay. Okay, so these are the set of numbers which we need to sort. And first, what we need to do is to build a heap or a heap tree with this set of numbers. So building a heap is basically we use the insert algorithm which we discussed earlier. Insert algorithm, what we are supposed to insert one node into an existing heap tree. So here we start with the first number, okay, 23, and let us say we have this is an array we are going to use, uh, or we'll draw it like this. Okay, we have an array like this where we are going to store our heap. We said this is an array representation, right? So we have starting at 1, index 1, 2, 3, let us say this is an array which we have. So in order to build the heap, first we are inserting the first element 2. So this is a complete binary tree, right? At location 1, we are adding 23. Or logically we can say we have created one node, which is the root 23. Okay. Now we know we have to add the next number. We are going to, so this is a heap because we know it is a complete binary tree and it does not violate any heap property. So this is a heap with single node. Now we are going to add 67, insert 67. So 67 we know since it's a complete binary tree, at the next level as the leftmost node we are going to insert 67, which means we'll insert here, or if you look at this, the next free location, you're going to insert it at this point. Okay, now we need to look at the if there is any violation. So of course there is a violation here, right? So 67 is greater than 23. So what we said is we need to swap this. Okay, we need to swap the values. Okay, so here also we need to swap, right? So now here we have a value of 67 and 23 goes here. Okay, so we have swapped, or again here also we have 23 here and 67 here. Okay, now next is 45. 45, what we do is since it's a complete binary tree, we are adding here, or logically it is actually 45 has to be added here. Okay, so 45 add. Now we are checking whether this is whether there is a violation. So here 67 is here, it is greater than its children, so there is no violation. So we will move on to the next number, which is 1. 1 we put here, or it is as leftmost node in the next level. So 1 is here, again no violation. 11 is here, again no violation. Okay, now when 99 comes, we are supposed to add it here. Okay, 99 is to be added here, or at this location. Now again there, since there is a violation, what did we say? We have to swap. Okay, so we need to swap 99. Okay, we need to swap this and this. So 45 comes here, 99 comes here. Logically speaking, uh, 45 comes here. Okay, and 99 comes here. Okay, now again you're checking. So again you have a violation. So 67 has to come here. 67 comes here and 99 comes here. Okay. So this again here you cut this. 67 comes here, and at location here at location 1 you have 99. So finally the list of numbers you have is 99 followed by 23. Then you have 67, 1, 11, 45. Okay, this is the final list after we build the heap. Violation undo. Here you have got 99. 99 is here. Then its child is 23, which is less than it. 67 is also less. Okay, so you don't have any violation. 23 has children 11, 1 and 11, which has lesser values, right? Similarly 67 and 45. So there is no violation. Okay, so this is the final heap which we get after building a heap using these set of numbers. So once we build, what we can see is the largest number actually comes at location 1. Okay, so that is what happens. Okay, okay, so this is a set of numbers. Now to do heap sort, what you do is to heap sort, what you do is you bring this to the last. That is, you swap 99 and 45. Okay, so we are going to do an ascending order sorting, which means the biggest number has to come last, right? So we know the biggest number in the case of a heap is at the root location. So we swap that and the last number, which means now we have 45 here, 23, 67, 1, 11, and finally you have 99. Now what we do is, so we know this number is actually sorted, right? So we don't consider it as part of the heap. Now what we say is we look at these set of numbers and we check. Now we have swapped this, right? 45 is at the root. We check whether there is a violation. Okay, so you check its children. 45 in the children is at 2i and 2i plus 1, which means you look at its child 67 has a greater value, which means you need to swap this and this. Okay, ഇതിങ്ങനെ swap ചെയ്താലേ heap ആവുള്ളൂ. Okay, so you have 67, 23, 45, 1, 11. Now 45 ആണ് ഇപ്പോൾ നമ്മൾ ചേഞ്ച് ചെയ്തത്. അതിൻ്റെ children they are okay, right? അപ്പോൾ അതുകൊണ്ട് this is the final heap in the next iteration. Sorry. Okay, next iteration, this is the heap. Now this is the largest value. So now you swap 67 and 11. Okay, 11 ഇവിടെ വരും, 67 ഇവിടെ വരും. Now you know 67 and 99 are sorted. You don't consider that as part of the heap. Now you look at the rest of the elements and again you heapify, apply the heapify process and keep iterating. Okay. Okay, so given a set of numbers, what we have to do is first we have to build a heap tree. Then you have to delete the root node from the heap tree and it will be placed at the as the last. Okay, and then rebuild the heap and you keep repeating this until heap tree is empty. Okay, so this is the overall picture. Okay, this is an example given in the textbook. So this is our initial heap, that is you have 99, 98, 69, 65. Okay, this is a heap. Now then what you do is 99 and 76 are swapped. So 76 comes here, 99 has to come here. I think this is wrong. Here you will have 99, and then after that what we do is, okay, 99 comes here, look, and then you consider this part to be sorted. You only consider the remaining elements. Then you have to heapify this. Heapify means you look at 76 and its children. You know 98 and 96 are greater, so you swap this. 98 comes here and 76 comes here. Okay, so 98 comes here, 76 comes here. Now again you check 76 and its children whether it is a heap. So we know that there is also violation here. So you can have 85 here and 76 here. Okay. So this is how we do the heapify process. Now there is no violation because 99 is not part of the heap. So now again 98 is the largest number within the heap. So you can swap 98 and the last element. So 98 is here and 14 are swapped and so on. So that is how you go about doing this. Okay. Okay, look, 98 and 14 are swapped. Then after that, look, 98 and 99 are sorted. Now uh, this is the remaining set of elements. Okay. So 14 was at the top, then you do a heapify to get this set of elements with where you have 85 at the top. So you swap 85 and 47. So 47 come here, 85 goes there. So like that you keep repeating. So that is the process. Okay. I had the algorithm also. Okay, so this is the algorithm for heap sort. So first you have a set of n numbers and output is it has to be sorted in ascending order. Array A is the data structure is used. So first of all you have to build a max heap from this array A. Build a max heap means you have to take one element and keep inserting. So insert heap algorithm we already saw. So take one element and insert it in the heap and finally you have a heap available. So that is a build heap algorithm. After build heap algorithm, what happens is you will have the maximum element of the set of numbers at location 1 or the root. Okay. Now what you do is I is equal to n. Now while I less than 1, what you do is swap 1 and I. 1 and n are swapped. Okay, you swap 1 and n. The first element contains the biggest value and that is placed at last and the last element is brought in. Okay. Now you say I is equal to I minus 1. So which means you don't consider the nth element any longer as part of your heap. Now what we do is now our swapped element is at 1. So you said j is equal to 1 and try to what you there is a violation. When you do a swap there is a violation, right? So first at location 1 whatever element is there it is swapped from the last element. So there is a violation there. So you have to rectify that violation. That is what is done in this while loop. Okay. So while I less than j less than I do, you look at the left child and the right child. Okay. And you find out from among the left child and the right child of j, you find which is the larger and you swap with j. Okay. That is what is done here. So if aj is less than a of left child, and a of left child is greater than a of right child. So if a of left child is greater than all the three elements, then you swap and you set j is equal to left child because now you have swapped the last, that is something like this. Here we said that is once you are bringing 98 here, you are swapping with this. Okay, now 85 comes here. Now it has to be checked with its children. That has to be repeatedly or iteratively done. So that is what. Okay, so so this condition checks which of the children are larger ones, and if it is uh, greater than the node itself, then you do a swap. Otherwise, if aj, that is a current element, is less than the right child and the right child is greater than the left child, which means you have to swap aj and the right child, right? Okay, now you set j is equal to r child. So keep repeating until you reach the last element, that is I minus 1. That is in the current case it is n, you started with n, now it is n minus 1. Repeat this. Okay. So with that we'll finish with heap sort.